I'm Guy Kramer, President and CEO of Hyperstealth Biotechnology Corporation, and in 2010 I figured out invisibility. Quantum stealth is a patent-pending light-bending material that works by bending the light so that only the background is visible and a target, such as a person, is removed from view when behind this material. I've taken the camera off the tripod at this point and I'm lowering it down to the floor, and what I want you to notice is how the horizontal wall molding still lines up. This is due to the fact that the material is perspective dependent, which means it matches your view and will be different for someone else. To reduce the visibility of a target, there needs to be some distance between the target and the material. This can also be demonstrated with the thin support pole behind the material. As you can see, it's nearly touching the material at the top, but it's about 8 inches away at the bottom. This causes the pole to be seen in the top half and disappear in the bottom half when viewed from the front. In version 1, as the material is polarized, it removes vertical elements and retains horizontal items such as the wall molding. In this test, there is no anti-reflective coating on this material. I was standing a few feet back in the previous video. If I was a little farther back, you would not see any indication that someone might be standing there. I have also determined a number of ways for the target to see through the material that are not shown here. This material can be as thin as paper and requires no power source. No longer do you need multiple camouflage patterns to match multiple backgrounds. One piece of this material can work in any environment, in any season, and at any time of the day or night. The reason you're seeing a green color in this video is that I'm recording with a night vision tube which converts infrared light to visible light. Most military night vision devices use the same frequencies used here. As you can see, the material is able to hide a target in this part of the night vision spectrum. Here I'm demonstrating version 1 of the material on a riot shield. This allows the target to remain hidden while moving or stationary. The material also makes aiming at the person's critical points, such as the head and chest, much more difficult. In the initial part of this video, my torso is somewhat visible, but as I hold the material farther out to create a greater standoff distance, the torso is nearly invisible, and with a little more distance it would be completely removed. Newer versions allow the target to get closer to the material. This video was taken through a special ultraviolet scope that records in the near and medium ultraviolet spectrum. Recently, more optics are using ultraviolet scopes and cameras for security and military purposes, as many camouflage fabric inks don't function well in this part of the spectrum. To show the ultraviolet bending limits, I'm pulling the material close to me. Only when I'm near the material can you see me. As demonstrated here, the material is bending the ultraviolet as it does with the visible and near-infrared spectrums. In order to understand the shortwave infrared spectrum, we first need to look at the visible spectrum. I'm wearing a currently issued US Army camouflage jacket to show how this can blend in reasonably well to the background here. We've already established that our material functions in this spectrum, and at one point I hold the shield with the material close enough that you can see me through it. When we switch to the near-infrared spectrum, or NIR, The camouflage is significantly brighter than the background, and you're no longer hidden to an enemy using the standard military night vision optics. I've used infrared lights to illuminate this area, and while it makes the camouflage stand out, our material is still bending the infrared light at this part of the spectrum. Going deeper into the infrared spectrum, the shortwave infrared or SWIR night vision is usually limited to elite special forces teams due to the high cost of these night vision optics, which can run in the tens of thousands of dollars per unit. This is because the majority of camouflage inks and colors don't function in this spectrum, allowing the special forces to easily identify the enemy at night. Their laser designators and aiming lasers also operate in this frequency, allowing only for their equipped forces to see them, as the opposing forces are unlikely to have these SWIR optics capabilities. As you can see, the material is bending the shortwave infrared spectrum. New fully digital night vision devices allow for daytime use, as there's no intensifier tube that can be damaged by sunlight or bright lights. This can easily identify certain camouflage patterns that may function well in the visible spectrum but don't function well in the infrared spectrum. A thermal imager allows the user to see temperatures and can easily identify a warm person in relation to a cold background. This video demonstrates how our material can mask the thermal signature of a human target behind the material. The US military recently began a program which will eventually provide all ground troops with enhanced night vision goggles, which combine near-infrared sensors with thermal imaging, allowing them to see most adversaries in combat conditions. Our light-bending material bends the near-ultraviolet, visible, near-infrared, and shortwave infrared spectrums, and blocks the thermal spectrum. Their new enhanced night vision goggles will not allow them to see a target behind this material. Conversely, US ground troops using this material won't be easily detected by opposing forces. Here I'm using version 1 of the material to hide a parked M1 Abrams battle tank. This is just a small remote control tank, but if I can do it small scale, the material can be scaled up to hide a real M1 tank. I wanted to find a way to hide a tank from aircraft, drones, or satellites overhead while it was still moving. The simple solution was to place one piece of the material on top of the tank with an appropriate standoff distance to allow room for the light to bend. Notice you cannot see the shadow of the tank's large gun on the ground. There are 11 halogen lights in the room, so there are numerous shadows of the material, but not the tank. If there was only one light source like the sun, the shadow the material creates is minimal. Notice while you're watching this that you can see right through the material to the other side of the desk and through the windows. This demonstrates that we can hide a target in 360 degrees. This would be useful for submarine periscopes and the newer photonic masts, as well as communication antennas, radars, and other sensitive intelligence gathering assets that need to remain hidden. When I point a laser at the material, notice how the laser stretches into a horizontal line. It's fanning out, and while the black tube blocks part of the laser line on the inside of the cylinder, it only has a very minimal impact on the laser line on the outside of the material cylinder. It's as if the laser line is going through the black tube unimpeded. If your concern is only from head-on identification, then the target to be hidden doesn't really need to be inside. It could be placed behind the cylinder. You may be familiar with the 3D effect you get when you move from side to side from something called a lenticular lens, which is a series of small, long lenses that run parallel to one another. This is precisely what I'm using for version 1, a single lenticular lens without a lenticular image behind it. Because lenticular lenses typically run in one direction, if you place a vertical object at a distance from the lens, when also positioned vertically, that object will disappear from the viewer's perspective. If the object is turned horizontally, it becomes visible through the lens. Figure 1 is a diagram illustrating the principle of the law of refraction as it relates to visible light. This is also referred to as Snell's law. When a light ray travels from one medium such as air and enters a second medium such as water, the light ray is refracted in a different trajectory. Figure 2 is a cross-section diagram of a lenticular lens sheet which includes a plurality of lenses or lenticules. Images from the lenticular lenses can be viewed within a V-shaped viewing region that corresponds to a viewing angle, and that viewing angle changes depending on the lens size and shape. Figure 3a is part of my discovery, which shows what takes place when a light source, 302, provides illumination to a sheet of lenticular lenses, 306, and the light ray, 308, from the light source passes through the lens sheet and a subset of light rays, 312, is refracted from the lenticular lenses in numerous directions. If the lens sheet was not there, the light ray 308 would continue to the path of 308b. Figure 6 demonstrates how a lenticular lens sheet refracts the light rays to actually create a dead spot to hide a target in. Figure 8 shows how to line up the lenses in a vertical orientation, placing a person standing up within this dead zone to reduce or remove the person from view. One drawback of version 1 is how blurry it is when there's a detailed background behind it. Version 2 shows the background detail because it works differently than version 1. Notice the white Hummer on the left, but can you see the camouflaged Hummer behind the material? Or the bright red one beside it? If the target's too wide or too close to the material, it only becomes partially invisible. This is a prototype of version 2. As you can see, version 2 demonstrates a very detailed background. However, the background objects at a particular distance become reversed or appear in mirror image. Notice the car in the background is facing the wrong way through the material. The reason for this is due to the assembly of the lenticular lenses, as I've placed 2 lens sheets back to back with the lenses running in the same direction. In figure 3C, you can see how this new double-sided lenticular lens causes light rays to intersect at point 1310. This is the same effect that water has when in a clear bottle or glass. The word is reversed when beyond the intersection point. It is the intersection point that causes a viewer to see the word and logo flip, and you may notice the heavy distortion at that point. This is a prime area to hide a target. But there's another advantage to version 2. The ability to move the background in the lens to the left or right by changing the 2 lens sheets and offsetting them from one another. Okay, so I have version 2 here, and I've got a colored marker line on one piece of the material, and I've marked the second piece of material with a different color there, just to show how little movement is required to offset this material. So you can see up here, you've got the 2 pieces of material. There's water in between. You can see the van here, the picnic table here. Here you've got the van and the picnic table. And if I had curved this material towards me, it would look less distorted. But if I pull the material towards the right, I'm gonna move the background. So I'm gonna hold this up here and just show you that by doing that, what I've done is I've moved the picnic table over here and the van over here. You can still see there in the middle here. In the middle, we actually have this neutral zone right about here. And it's picking up the trees from over here and the trees from over here and merging them into the middle. You can hide a target in here, or you can take a target like this van and just completely move it out of the field of view. And so if we look now, we can't see the van in there, and yet the van is right there. So that's what the offset is doing, and it's just slightly moving. So you're just getting those 2 lenses changing just ever so slightly in order to do that. In version 2, the third way to hide a target is utilizing the neutral section. Here I'm holding up version 2 and placing my hand in behind. As you can see, at a minimal distance behind the neutral section or neutral zone, the hand disappears. Version 2 is simply putting 2 version 1s together. Now there's a smooth side and a rough side. And what we're doing is we're putting the 2 smooth sides together. And I'm using water to bond the 2 pieces together. The ideal situation with version 2 would actually be to create it as one piece, manufacture it as one piece. But I don't have the ability to manufacture, nor did I want to go to a manufacturer to get them to build this special material, right? They would have started to clue into, hey, this is the guy that keeps talking about invisibility. I wonder if it's this material. And if I disclose too much, perhaps they may have talked to someone. I just couldn't risk it. And so the patents were only filed a couple of weeks ago. And only now do I have the ability to go to a manufacturer and say, this is what I'm looking for. So again, I apologize for the crudeness of this material and that it may not be as detailed as you would like. But if it was manufactured properly, you would see a crystal clear image behind me through this version 2. This is version 2 large-scale testing. I've aligned the material so the neutral zone is not in the center of the material. This creates dead spots on the two sides of the material to hide targets. Also notice how my image is moving in the same direction when I'm close to the material, but is moving in the opposite direction when I'm farther away. The point at which this switch happens is the flip point, and at that point, even if you did see an indication of the target, it is so distorted that you would probably not be able to identify what the target was. In the next test, I've shifted the neutral zone to the center of the material. This creates a dead zone in the middle of the material in which to hide a target. This is version 2, and as you can see, it's much better than version 1 at hiding objects behind it, as it provides a detailed background, the target can get much closer to the material before being detectable, and it's removing both the horizontal and vertical components of the target. I could edit these videos to make this much more impressive than it actually is, as there's a drawback to the cylinder or tightly curved approach in that it only hides the target at specific viewing angles and enlarges the target at equidistant or equal distance viewing angles. If you're a fan of science fiction, you've probably heard the term phase shift. This is where an object such as a spacecraft in phase can be seen and out of phase becomes cloaked or invisible to anyone outside the craft. The fictional part of this is that until now, we didn't actually have that ability. The term phase shift is also used in physics and typically refers to small-scale or quantum physics. A phase shift occurs when two identical light waves travel to the same point, but they travel different distances to reach that point. If the light wave started out in phase, they will be out of phase at the destination. If the crest of one wave lines up with the trough of the other, in other words, their waves are completely opposite to each other, then they cancel both waves out. This is known as destructive interference. While the term phase shifting seems appropriate for this effect, scientifically that's not what's occurring here. The laser is demonstrating what's happening to the light rays through the double-sided lens. When the target is out of phase, the laser is splitting into two parts, with each laser refracting at 40 degrees, meaning that what you're seeing is the background image 40 degrees to the left and the background image 40 degrees to the right converging to create a neutral zone, and the target is invisible. When the laser is within the in-phase section, the two lasers now converge onto the target, but magnifying the target size to the viewer. If we know what specific direction the viewer will be at, such as hiding a police officer at the side of the road from oncoming traffic, as the police use their radar or lasers to determine oncoming vehicle speed, as the vehicles get closer past the speed detection area, the angle changes and they see a magnified view of the police officer, allowing for the safety the police require so no vehicle accidentally hits them. Then this could be a reasonable solution to removing the target from view. Within the patent, I've allowed for the manufacture of this material so the majority only shows the out-of-phase sections, and the in-phase sections would be so minimal that the target would be unidentifiable. We could manufacture the material entirely in the out-of-phase viewing angle, but this would reduce the overall detail we currently have with version 2. version 3 now, and version 3 is simply two version 2s put together. And the reason we need to do that is when you look at that truck in the background there, and look here, it's facing the wrong way. And we need to fix that orientation. And in order to do so, what I've done is I've got two version 2s stuck together. They're the same, they're 60 LPI. This would be much clearer with 100 LPI or 200, but it's easier for me to work with and film with the 60 because it's so rigid. And so there's the truck there in the right orientation, and yet it's over here. So we can actually offset this and correct this the same way we can with version 2. It's still got the same neutral zones, so I can still shift the image on there and get it to line up or move it right out of the field of view. So it's version 3 is improved over version 2 in a number of ways. The most critical being that the correct orientation is now displayed, and it doesn't distort if you go back further. As you can see from these pattern figures, version 3 operates differently than version 2. No longer do the light rays intersect, but they run parallel to each other, meaning the background appears as it should in the right orientation. I can no longer hide a target within the intersection distance as I could with version 2. I can still utilize the neutral zones and/or shift one or both of the double-sided lenses to move the target out of the field of view. I've shifted the material offset so the background is shifted right to allow me to hide on the left side. At 40 inches away from the material, I'm completely removed. At 20 inches away, you can begin to see my shoulder. Only at 10 inches does the target come into view, and even then there's a distortion present that makes identifying the target difficult. Version 4 is simply like version 2, but the lenses are different. So here I've got a 30 LPI, 30 lenses per inch, or lenticules per inch, and on the other side I've got 60 lenses per inch. This creates a different field of view. So rather than seeing the exact image at the exact scale in the background, it actually creates something that shrinks everything down. Something odd begins to happen when we use larger sheets. The background repeats in long, narrow parts. They look identical, but they are not, as each part is a slightly different angled perspective of the same background. To correct for this, we can curve the material to stretch each part to allow it to match the apparent aspect ratio of the background objects. The viewer moving will create an anomaly of movement on the lens. And if I flip the material so that now the big lens is towards you and the little lens is away, now you're going to see a smaller field of view through the material than you would out of version 2. The image on the left is version 4, and the image on the right is version 5. And it's obvious there's a marked difference between the two of them. Version 4 has the correct perspective, but it creates a lot of movement when the viewer is moving side to side. Version 5 on the right is much more stable to the viewer's side-to-side movements, but everything in the background is now reversed. The background also repeats in version 5, but even more extreme than version 4. Curving the material makes little difference to the narrow repeating parts, but there's something special happening here that I'll get back to in just over a minute. Here I have two version 4s. And to make version 6, we simply place both version 4s together. Version 6 as well as version 3 are very difficult to work with in this prototype stage, as not only do I need to line up each lens that makes up each double-sided piece, I also need to line up the two double-sided pieces in relation to each other, and I have to do this without a liquid to bond them together, as a liquid in between the two double-sided sheets nullifies the lenticular lenses that are touching each other as it fills in the gaps between the lenses that are necessary for the light bending. I can bond the smooth sides of each sheet together, but not the lens side. If manufactured properly, there would be no ripples in this material. Curving version 6 can correct for some of the distortions and begin to match the aspect ratio of the background. Version 7 is two pair of version 5s with one in front of the other. This corrects the orientation of the background and removes the multiple images. Version 8 places the larger lenses in the middle and the smaller lenses on the outside. The results are visually similar to version 5. And version 9 places the smaller lenses in the middle and the larger lenses on the outside. The results are visually similar to version 4. When we have a slightly different perspective of version 5 and version 4 when I turn it around, the material seems to be emulating the shape of a lenticular lens and refracting the background the same way as miniature lenticules do in version 1. It's as if we have a large lenticular sheet that should be inches thick, but it's only as thin as a piece of cardboard. This means we can hide larger items such as tanks, ships, buildings, aircraft hangars, and such with this thin, inexpensive material. If we had just scaled up versions 1, 2, 3, and beyond, the material would be very expensive and almost too heavy for most applications. When I started to experiment with different size lenses on either side of a double-sided lens, these combinations became version 4 and 5. I began to run into repeating interference patterns which seemed to make the lens useless in almost all applications. I could often curve the material to remove most of the repetition. I didn't fully understand why this was occurring until I put a certain combination of lenses together, which in turn created just over 100 of these repeats across 28 inches. But the lenses on one sheet were 100 lenses per inch and the other sheet was only 25% larger. But this appeared like 3.7 lines per inch, which is 27 times larger than one of the sheets and 20 times larger than the second sheet. If it was emulating the smaller lens in a larger format, did it behave the same way as the smaller lens? When I held it so the lenses were running vertically, it removed the vertical window frame from view, and when I turned it so the lenses ran horizontally, it showed the vertical window frame and flagpole outside, but removed the horizontal window frame. It had the same effect on the background as a single lenticular sheet would. This caused me to go back and look at my previous test to the large repeats of 6 or 8 across 28 inches, to allow me to figure out what was occurring here and there. The combination of two different types of lenses was causing an interference pattern on each side of the material, and it wasn't the same pattern on each side. It can be thought of as a resonance between the two different types of lenses. These large repeats were simply the same as the 3.7 per inch, but due to the particular lens combination I used, it generated a resonant of 1.5 lenses per foot. I am naming this newly understood effect remark, which stands for Resonant Elongated Magnifying Abbreviated Repeating Curves. When we have a slightly different view of version 5 with two very closely related lenses per inch, and version 4 when I turn it around, you can see this larger remark effect. To duplicate this effect by scaling up version 1, the lens would need to be inches thick to accomplish this, and yet to do the same thing this material is as thin as a piece of cardboard. When I use particular combinations of version 2 where both back-to-back lenses are identical, the remark effect is about 28 inches across, as can be seen in these next two videos. In the first video, I've moved the edges of the arc to either side, and in the second video, I moved the edge of the arc, or neutral zone, to the middle. In other words, this is emulating scaling up 100 lenses per inch version 1 by 2,828 times, and that lens, if scaled up, would be 39.6 inches thick and 28 inches wide and weigh about half a ton or 1,000 pounds. To hide an M1 Abrams tank by scaling up version 1, the material would need to be close to an inch thick and would weigh close to 5 tons and require expensive engineering to support that weight. The Remark Effect version would weigh in at about a quarter ton or 500 pounds in its current form, be as thin as cardboard, and as it's just over 1 pound per square foot, would not require expensive engineering to fix it to the tank. Given that an Abrams tank costs about $8.5 million, and this material can make it invisible from ultraviolet through the entire visible spectrum all the way to the shortwave infrared and block the thermal signature, this thin Remark version of our material would be a practical addition. Inexpensive aircraft hangars using this material could hide the new $100 million F-35 fighter jet at an airbase, or even the $250 million F-22, or the massively expensive B-2 stealth bomber that costs a whopping $2.2 billion per aircraft. If we were only able to scale up our versions, it would have been impractical to hide larger critical military equipment, such as vehicles, ships, and structures, due to the heavy weight and high costs. However, the Remark Effect should change that. For the following demonstration, I'm using the background in Figure 34 to simulate the effect on the lens sheets shown for versions 10, 11, and 12. Version 10, shown in Figure 35, has a base lens in the vertical polarity and several angled sections of sublenses where the sublenses have different angles than the base lens. One angle of sublenses in section 3502 is slightly left of vertical and appears on about half the shapes, while the other half are slightly right of vertical. Figure 36 simulates how version 10 would depict a blurred background image having different types of artifacts caused by the corresponding angle sections 3502. This can easily be done where the lens material is manufactured by a mold on a drum, whereby the mold would have all the different angles formed on it. Version 11, shown in Figure 37, better represents more natural geometric shapes for use in many outdoor woodland-type backgrounds. Figure 38 is a simulated image of Figure 37 depicting a blurred background having different types of artifacts caused by the corresponding complex sections. This has a similar effect to camouflage, to break up the background so the material does not appear to be an anomaly to the viewer. Unlike static camouflage where the colors are predetermined, the added benefit here is that all the lenses are still pulling surrounding colors from the background. Although a single angle is used for the arrangement of sublenses in section 3702 for the pattern, more than one angle may be used to increase the realism. In addition, lens sheets other than single-sided lenses may be utilized. Version 12 is shown in Figure 39. Here the base lenses are made up of one type of LPI, or lenticules per inch, and the sublenses are using a different LPI. The different LPIs achieve a similar effect to the angled arrangement of sublenses. Figure 40 is a simulation of version 12. The base lenses may be a narrow angle, while the sublenses may be wide-angle lenses of the same LPI. Conversely, the base lenses may be wide-angle, while the sublenses may be narrow-angle of the same LPI. The sublenses may have a different LPI, or a different angle of the base lenses, and there may be more than one sublens with different LPI and/or different angles. Figure 41 is a view of Figure 39 placed in front of a background depicting improved concealment. The black vertical lines are for illustration of the polarity only, and would not be discernible to the viewer. The patterns used on the sublenses to disrupt the background may be specific to the environment. For urban environments, angles representative of walls, floors, or stairs may be used. For arid or desert environments, sparse disruption would be used. version 13 basically takes the advantage of this material when we start to offset it, that we start to distort the target in behind. And so now you can see there's something weird happening there, because what I've done is I've actually changed the angle of the two lenses in relation to each other. And yeah, you can see something odd is happening, but try and guess if that's a human being or an animal or another target you're trying to hide, and it becomes nearly impossible. And the reason for this version initially was underwater. All these versions work, but you have to be farther away than you do in air because water bends light. And so that refractive index of water has to be factored into this. And so in certain applications, such as a Navy diver using this, where they're trying to hide them coming up on a beach from overhead view, whether it's a ship or observation tower or drones or whatever, something flying over, trying to identify threats. The diver doesn't want to be seen or targeted. And so having a piece of material that's too far away just wouldn't work for them. So we can get it really close. I'm actually holding that right onto my torso, and it's still distorting it. And so now the observer above cannot identify what it's looking at, and with water you're unlikely to even notice something is down there unless it's solid, right? Well, this doesn't look solid, and so you have enough of this, and we can manipulate the lenses and the angles and everything to configure something that looks better than this. That's where that idea initially came from. But that idea may be applicable to M1 Abrams tank, where this material in the correct configuration, right? Let me just move my body out of there. Sorry, I'm getting a reflection of the lights here too. This may need to be 12 feet away from the tank in order to have this effect on the tank. And so it depends on the width of the object. So a tank is very long and very wide. And in my initial experiments, we were finding that we can do it. We can make a tank completely invisible. Version 1, we can be closer, make it invisible, but it doesn't give that detailed background that you might be looking for. Version 2, need to be about 12 feet away. If you get closer, about 6 to 9 feet, you get a distortion effect happening with version 2, but you can still see something kind of like a tank. But when you start to change this and angle it, now you can't, you know something's there, but your brain is going, I can't connect the dots. I don't know what it is. there was a room full of probably about 15 individuals. And one individual in particular looked at version 1. Well, I turned to him and I said, what are your rules of acquisition of a target, and are you allowed to fire on something if you haven't identified it yet? And he looked down the table towards the commanding officer and he looked at me and he goes, no. And I said, for all you know, it could be a school bus or a baby, right? So until you can identify what the target is, you can't shoot at it. But if I'm using this material and watching you, I have all the time in the world to figure out where you are, what the threat might be, are there others of you, and either observe or take action. And take action before you have the ability to even figure out what you're up against. Are you fighting a single individual, a platoon, an army, a tank? You don't know. And you're still not going to know until after I start firing and you're hearing, okay, I hear one gunshot or one particular type of gun. I'm probably dealing with an individual. But it doesn't make it any easier if I'm able to move around and you can't see any indication that I'm moving behind this material, right? Or moving with this material. And again, version 2 and version 3 would probably be better examples for that. How thin and pliable can the material be? The answer is very. Can we use other lenses that are not made up of lenticules? Yes, we can use one-angle prism lenses as seen in figure 11, and while we don't show another figure in the patent, we do describe adding another single angle in the reverse angle on the right to allow the target to hide in the middle. We can also use two-angle prism lenses. Or we could use something called a dove prism lens, and if we split the lens down the middle, a half dove prism lens, which are not shown here. The half lenses would be similar to version 2, which are the double-sided lenticular lenses. This provides 5 different types of lenses that can be used in most of the 13 versions. But we're not done there. Now that I know what's occurring, we've added the ability to custom manufacture lenses with different lenses per inch, as shown in figure 63. And or different angles of the lenses to provide optimal concealment for future versions. A question that comes up a lot in the demonstrations is how does the target see through the material? We can perforate the material, which is similar to the vinyl advertising wraps that they use on bus windows, so the passengers can see out the window while the people outside see the advertising. Or we can create larger holes while still retaining structural integrity. There are numerous ways that the material may be applied in place of pre-existing privacy inserts, covers, camouflage nets, parachute material, pop-up tents, inflatable structures, clear corrugated material, with or without support structures, and so on. I've applied version 1 of the material to a drone to see if it could safely fly, and see if it was able to reduce the signature of the drone. Most applications for a drone are going to be above the person or persons of interest, which is why the material here is to hide a view from below at an angle, so there's no need to cover the top portion in this example. There will be small-scale applications where you want your vehicle to be seen for reasons of security, but you don't want an individual who has to be out in the open to be visible to others. You could place the material in cylinder form around them or beside them to hide their presence from others, removing some of the vulnerability that that position often requires. Cellular towers, wind turbines, and communication antennas are problematic in that aircraft need to see them for safety, but the public doesn't enjoy seeing them in the middle of a natural setting. So how do we hide them so that you can't see them from the ground, but the aircraft can see them from above? With our material, this is now possible. The lenses are periodically placed above one another, so to the person on the ground, the bulk of the tower vanishes, but the aircraft above can still identify the majority of the tower. Another way to remove a target is to bend the material, causing so much of a distortion that it appears to flatten the target. As I'm using the lens horizontally, the sky is being shown upside down, so this is not likely to be practical for ground operations. But a naval vessel could potentially utilize this technique to hide it from pirates, enemy observers, or smart weapons that often use a number of spectrums, such as visible and thermal, to target the ship. What's the future for quantum stealth? You ain't seen nothing yet.